Welcome back, everybody. AP Chemistry. We're looking at Unit 2, Section 2. And where we left off in Section 1 was looking at certainly the Lewis structures and everything, but we left off with the concept of resonance structures. And so that means that there are alternatives out there for making a compound. And so the question is, how are we supposed to know which one is actually more likely to be formed? And so the answer to that is going to be formal charge. And so just kind of continuing on with the notes, and like I said, it is possible sometimes, at least theoretically, to have two different or more different structures on there, and we can actually figure out which one is the correct one based off of this equation. Now, this looks really daunting. Don't be thrown by this because it's just a method of tracking where the electrons are and which one would be more common. So this is going to be my force that's in there, okay, the formal charge that's in there, and the X is going to be the valence electrons in the free atom. So let's do an example of one of those with something pretty simple that's just going to be nitrogen trifluoride. So nitrogen has 5 valence electrons, and fluorine has 7 valence electrons, and we have 3 of them, so that's going to be 21 plus 5, so that's 26 total electrons. Okay, so let's draw that out. We have 2, 4, 6, and let's fill up my peripheries, 8, 10, 12, 14, 16, 18, 20, 22, 24, and then looking around my nitrogen, we have 2 more electrons to get in there to fill out the octet. Okay, so now we've got all of my electrons accounted for. So X would be the valence electrons of the free atom. My free atom is going to be my nitrogen. I have 5 valence electrons there. Okay, so 5 valence electrons is going to be equal to that on the periodic table if you look at your columns and so on. Now, the number of unshared electrons owned by that atom. So here, remember, is my unshared electrons. Okay, so we're going to be taking a look. That's my Y value. So there are 2 of those. And then this last step, that Z value, is the number of bonding electrons shared by the atom in the Lewis, divided by 2. In other words, that one was with nitrogen. That's shared out, that shared out, that shared out. You could certainly count it as 2, 4, 6 and divide by 2, or just look at the 3 electrons that were shared out by nitrogen. And so that's going to be 3 electrons that were in there. And so we see that 5 minus 5 is 0. So the overall force that's going to be in here, the formal charge, is going to be a 0. Now, the closer to 0 it is, the more stable that's going to be. Okay, that's the one that's going to be actually thermodynamically favorable. So let's look at this example. And this one, I do have the molecules already in your student notes. I've got them already written out for you. So let's take a look at these. We have 2 options for methanol. Okay, so I'm just going to copy these down real quick. And then my B value is going to be hydrogen with a carbon, and my oxygen, hydrogen, and hydrogen, and then one last hydrogen right here. Okay, so we've got all of these structures in here. So the question is, which of these, even though these are both possible, which one is going to be the one that's more probable? Okay, so let's take a look first of all around here. The X value for my carbon, there are 4 valence electrons on this carbon, and so now I count up. Oh, there are 0 of my lone or unshared pairs. And around here I have 1, 2, 3, 4 shared pairs that are in there around that carbon. And so overall, 4 minus 4 is 0. If I look around the oxygen here, oxygen has 6 for valence electrons. I have 2 and 4 unshared pairs, and then 1, 2 shared. And so once again, with both of those, I have the formal charge of 0. Now, if I look around this option, okay, so keep those separate. I look around this option, once again, valence electrons is 4, and I see I have 2 unshared, and I have 1, 2, 3 shared. And so on this side, I see I have a -1 for formal charge. And now let's look around this oxygen. This is my carbon around the oxygen now. We have 6 valence electrons, and I have 2 unshared pair, and 1, 2, 3 shared. And so once on this one, I have a +1. Okay, so really we're seeing the closer to 0 is going to be more favorable, and so this would be my, even though both would work in theory, this one option would be the one that would be more likely to be formed, the most probable Lewis structure for that compound. Okay. Ordinarily, it's the one that's at closest to zero. And do note that any negative formal charge, in case both of them have something other than zero, the negative formal charge is located on the most electronegative atom. And so remember on here that I had around the carbon, I had a negative one, and around the oxygen, I had a positive one. Well, if you go back to your electronegativity charts, and I'm just going back to the very first page of our student notes, we saw that the electronegativity value for oxygen was 3.5 and the carbon was a 2.5. And so based on statement 2 as well, any negative formal charge is located on the most electronegative atom, and that is certainly not the case. It was around it was around carbon, which is not the most thermodynamically, not the most electronegative, I should say. Okay, so next concept, let's take a look at the formal charge for sulfur, or sorry, for sulfate. And notice that we have 2 electrons that are on the outside of all of that. Okay, so we got a little bit more work ahead of us. Let's take a look now at the Lewis structure and the options. Okay, so we have, first of all, we have SO4, we have a -2 here, so we have 2 electrons that we have to add into this compound. My sulfur ended up being, we have 6 valence electrons, and then we have 4 oxygens. And so that's 24, plus 6 is 30, plus 2 is 32 total electrons here. Okay, so we're going to have a couple of options here for my sulfate. Let's take a look at this one. We have sulfur. Get my oxygens in here. And so I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. And then on the outside, oops, I got off of my counting, but trust me, there's going to be 32 total electrons on there. All right, let's take a look now at option B. We could also do this in terms of double bonds. This is kind of an unconventional one. We see the oxygens here. And, oops, that's going to be my oxygen. And once again, we get 2 electrons. So the question is, this one's one that I probably would provide for you rather than trying to come up with the options on here. So we're trying to figure out which one is the more correct one. So if I take a look at this core, okay, sulfur has 6 valence electrons. Okay, so we're going to be taking a look, and I have 1, 2, 3, 4. So I have 0 unshared, and I have 4 shared. Okay, so that's going to be an overall formal charge of a +2. Now take a look at this one. We have, once again, 6 valence electrons. I have 0 unshared, and I have 1, 2, 3, 4, 5, 6 shared. Okay, so the double bond, we still count those in there. All right, so quite simply, we see 6 minus 6, we have 0 for my formal charge. That's going to be my most probable Lewis structure. Okay, so pretty straightforward once you get a feel for how these are going to go. And let's take a look at another example. And the 3 structures for xenon and oxygen. Okay, so I'm going to give those to you. We have option A. Oh, let me switch over to here. Option A is going to be, let's see, xenon with 2 unshared electrons. I've got oxygens here. I've got oxygen here, and oxygen here. Okay, so there's xenon. There's one option. Another option here would be xenon, and this time we would have, finish these up, and I would have a double bond on that oxygen. And then option C would be xenon. Why do I keep writing X? It should be Xe. And we should have double bonds all around. To do that, we would end up with just 2 electrons on each, 2 sets of electrons on each of the oxygen. Okay, so let's take a look at our options now. Xenon has valence electron of 8 because it is a noble gas. All right, then we take a look, and around the xenon, I have 2 unshared, and I have 1, 2, 3 shared. And so I have a formal charge of 3, and it's a plus 3. Look around this one, I see 8 minus my 2, and I have 1, 2, 3, 4. So there's 6, and so I have a formal charge of 2. And around this one, I see my valence electrons as 8. I have 2, and then 1, 2, 3, 4, 5, 6. And so 2 plus 6 is 8. 8 minus 8 is formal charge of 0. Pretty easy. We get option C is going to be the most likely one. Okay, so once you practice up that, just know the little tricks to a couple of those. We're good to go. It's not too bad at all. All right, moving on. Let's take a look now. There are some exceptions to these rules, and just know these things. We've seen a couple things in play already. You might have looked at that xenon and go, wait a minute, that's too many electrons and so on. Yes, there are going to be exceptions to these rules. The second row elements never exceed. So second row, that's going to be n equals 2. They never exceed there because we only have a 2ns and a 2p. They don't have any d's in there, and so that's where we start to find our exceptions. The second row elements of boron and beryllium often have fewer than 8. We find boron and beryllium are going to be just short of there, and so here's some examples of what I'm saying with that. If we put this into play, we see boron. Boron itself is going to have a valence electron of 3. And then fluorine has 7, so we have 3 times 7 is 21. That's 24 total electrons. Okay, so we go boron 2, 4, 6. Here's my fluorines, fluorines, and fluorines. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We're done. We have our 24 electrons in there. And notice boron only has 6 electrons around it. It does not get to the octet. Now I take a look at beryllium. Beryllium is a 2s2, so we have only 2 valence electrons here, and chlorine has 7. We have 2 of those, that's 14, plus another 2 is going to be 16 total electrons. Okay, so beryllium, and I have 2 and 4, 6, 8, 10, 12, 14, and 16. That's 16 total electrons, and it's done. Because it's a 2s2, that's all that's going to be in there. We don't get to our octet with that particular example. Okay, so pretty straightforward with that. Now, another one that we need to keep in mind is that third row. This is where it starts to get kind of interesting when we get our different shapes and everything. They're heavier elements. They often satisfy the octet rule, and they will go beyond that. Okay, they will be going past that. We saw that with xenon. We'll see it with a whole bunch of other things. Even if you go back to example 5, the sulfur within the sulfate itself violated those octets. All right, so let's take a look at some examples of those in play. All right, we have chlorine with fluoride. Okay, we have valence electron of 7, and then we have 3 of my fluorides with 7. That's 21. That's 28 total electrons. Okay, so let's go chlorine with my fluoride, fluoride, and fluoride. Okay, so that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And so the question is, wait a minute, what do I do with this? Because I have 24, I still have 4 more electrons to account for. Well, what happens is they must go around that chlorine here and here. And again, it's just one of those things. If I was going to draw this out, then this is going to get into the next section. We're going to see that chlorine has 2 unshared pairs, and then we get a fluoride here, a fluoride here, and a fluoride here. Now, certainly you wouldn't be expected to just come up with examples on this. I give you the compound, and you just must make it so. Now, let's take a look at this one with iodine and chlorine. All right, so iodine is in the exact same column, 17, so I have 7 valence electrons. Now, this time I have 4 chloride, so that's going to be 28, plus another 7. Okay, so that's 35, and one more is 36 total electrons. Okay, so if I was going to fit all of these in, I end up with iodine, and we're going to form it with, this time, 4 chlorines. Sorry, it's getting messy, but okay, so we have 2, 4, 6, 8, 10, 12, 14, 16, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. But I need 36. So there's going to be a couple more on these. And remember, we added in 1 extra electron because it is an ion. Okay, last one is going to be the triiodide. I'll just do that one over here. And so we have 3 iodines in there, and notice that it's an ion with the extra electron. So I have 3 times 7, okay, that's 21, plus 1 more is 22 total electrons. All right, so we have iodine, and we're going to form 3 of them. Okay, so, or we're going to combine 3 of them. So let's do that. And we have 22 total electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and we must have in there 1 more set that's going to be a 22. Okay, on the outside then, we would have 1 extra electron. Okay, so it's just violations to the general rule, which it's chemistry. Get used to that. That's going to happen quite often. All right, so this concept is feeding into the bigger thing, but you can start to see that we can explain some shapes on there. And when writing the Lewis structure for a molecule, first of all, satisfy the octet. Don't worry about those other exceptions along the way until you have to force in the extra electrons, then place them on the elements that have an available d orbital. Okay, so the element period 3 or beyond, that's all this is saying. All right, so this is going to be everything for section 2, and just kind of keep going with that same concept, and I think you'll find that formal charge isn't anything too bad. Good luck.